Okay, so for this video, we're looking at conservation and specifically momentum conservation through two different lenses. And we're going to do this in a way similar to what we may have done in class before, where over here on the left we have this simulation that will show us mass and velocity data for these two carts that will collide, both before as their initial velocities and then after their collision up here on this grid area. And then over on the right, we're just going to quickly sort of sketch out the situation before and after they collide in one of these diagrams that are really useful when we're trying to apply different conservation laws, whether that's momentum, energy, mass, or in rarer cases, maybe charge, for conservation of charge. So here we have on the left a red cart that is 3 kilograms, and it has an initial velocity of 4 meters per second, and that is positive 4 meters per second, which according to this simulation's coordinate system means that that velocity is heading to the right. And then we have another blue cart, which is 1 kilogram, and that initial velocity is negative 8 meters per second. And then negative in this coordinate system means that it is heading to the left. And you'll notice I'm going to draw that velocity vector, because remember these are velocity vectors and not force vectors. I'm going to draw that velocity vector as longer than the 4 meters per second one because 8 meters per second is faster. So a greater magnitude means a longer vector. Okay. Now, even though the simulation does not give this, we can initially solve for both of their momenta. And so in order to do that, we need to use our P equals mv equation, the standard momentum equation, so we can get that for our red cart. P equals mv, m being 3 kilograms, I have to excuse my handwriting, 3 kilograms times 4 meters per second will give us an initial momentum for this red object of 12 kilogram meters per second. And then for our blue object, we can do the same thing. We have a mass of 1 kilogram times a velocity of negative 8 meters per second, giving us an initial momentum for the blue object of negative 8 kilogram meters per second. Okay. And then this will be important later, but we can also solve for the total momentum in the system. So if we put these numbers together, so our 12 kilogram meters per second from the red object plus the negative 8 kilogram meters per second of the blue object, that will get us a total momentum of, I believe, 4 kilogram meters per second. And so again, where this 4 came from is just the adding up the red object's initial momentum plus the blue object's initial momentum. So 12 plus negative 8 gets us 4 kilogram meters per second. And in fact, I should put eyes on all these things to remind myself that these are all the initial momentum, the momentum before these objects actually collide. So let me go ahead and add those eyes. Okay. Now let's allow these carts to collide, and then I'm going to pause it right after so that we can collect the after data. Okay. So, things have changed here. So now we still have the same mass of this 3 kilogram object, of course. So still 3 kilograms. However, now its velocity is negative 2 meters per second. And for our blue object, it still has that same mass of 1 kilogram. Let me put that spot. 1 kilogram. And now it's moving with a velocity of positive 10 meters per second. Okay. And so now if we use this sort of theoretical data from a simulation, and we'll be testing this in class if we haven't already. But let's get each of these objects' final momentum. So I'm labeling this PF just to remind myself this is the final momentum as opposed to PI, our initial momentums. So we're just going to do the same thing. Momentum is mass times velocity, same mass of 3 kilograms, now times -2 meters per second, and that'll get us -6 kilogram meters per second. And then we'll do the same thing for the blue one. This momentum is 1 kilogram mass times 10 meters per second. And that'll give us 10 kilogram meters per second. Okay, so again, there are two different ways that we could look at this and analyze this as an example of momentum conservation. And the first way, the way that's more similar to how we've analyzed conservation in the past, is by getting the total momentum before and after. So if we take this -6 kilogram meters per second and add it with that positive 10 kilogram meters per second from the red object, -6 plus 10 would get us that same exact 4 kilogram meters per second at the end in total in the system as we had at the beginning. So that is sort of the first and maybe more standard way to view conservation, is by saying the total momentum in the system stays constant. And that would be the first way to think about momentum, is that the total amount of something in the system, whether it's momentum, energy, mass, charge, that total is remaining in the system. That is specific to closed or isolated systems, depending on what kind of conservation we're talking about. But that is one way to demonstrate conservation, or one way that conservation could be thought of. The other way is by thinking about what these objects are exchanging. So if we think about the changes in momentum here, I'll move this over a little bit. This red object goes from 12 to -6 kilogram meters per second. And so if I think about the change in momentum, that's our delta P, that equals, to go from 12 to -6, we had to lose 18 kilogram meters per second. So that's the change in momentum for the red object from before to after. To go from 12 to -6 kilogram meters per second, it had to lose 18 kilogram meters per second. And if you're wondering how I got that, it's always final minus initial. So to calculate a change like this, it's just our final momentum minus the initial momentum. So that would be this -6 as our final, -6 kilogram meters per second minus the 12 kilogram meters per second. That's where this number -18 came from. Then over on the blue side, we could do the same kind of analysis, where to go from -8 to 10 kilogram meters per second, we'd have to gain 18 kilogram meters per second of momentum. And that may sound somewhat familiar, because that is the exact same but opposite change in momentum for the red object. So whatever this red object lost, it lost 18 kilogram meters per second. The momentum that it lost was gained by this blue object. It gained 18 kilogram meters per second, and the red object lost 18 kilogram meters per second. So that's the second of these sort of two equivalent ways of looking at conservation, is whatever is lost by one object is gained by another. And that's true for mass, energy, charge, momentum, that if if something is conserved, it means the total amount stays constant, and whatever is lost or gained by one object is also either lost or gained by the other object. What's gained by one is lost by the other. And these are two really useful frames that we can use to analyze conservation, and we will use them frequently throughout this unit. But this is just the one specific to momentum.